Okay, well, it's 10:33. We are recording this message. Welcome everybody. I'm so happy you're here. Our first talk. So I'm Tina Adair. I'm on the community engagement team with Melissa Graham. And our other moderator, do you want to introduce yourself?
Hi everyone, I'm Márcio Catelan from Chile, and I'm here with Tina to conduct the Stars, Milky Way, and Local Group session.
So we have our friendly reminders, which everybody's been participating in these talks. So remember to make sure that you're asking questions on Slack or here in Zoom. It might be easier to ask them here in the chat in Zoom since I think the Slack channel is going to be inundated with everybody's stuff. So are we ready to get started, Márcio?
Yeah, sure.
Okay, everybody else good? Who's our first person? All right, here we go.
You will see a timer in my background, okay? So
perfect, that sounds wonderful. Okay, thank you. All right, well, I'm excited to kick this off. I think I'm going to start with the largest scale here with the local volume, if we could. I wanted to speak about a really exciting science opportunity that Rubin Observatory is going to be able to grant everyone. And this is, will we be able to reveal the presence of synchronized star formation in galaxies? This is based really off a study that we just published back in May, where we actually found evidence of synchronized star formation in star formation histories of local volume dwarf galaxies. And for these local volume dwarf galaxies, these were from archival HST observations for the most part. This was a sample from the ACS Nearby Galaxy Survey Treasury, which is the ANCS sample. It's a volume limited survey, but only pushes out to about 4 megaparsecs in the local volume. But these had, they were far enough away to where we could get really careful integrated photometry, but close enough to where we could resolve individual stars. It's important for our analysis. As you can see on the next slide, what we were doing is really comparing two methods of star formation history reconstruction. One from resolved stars, which was the CMDs, and one from integrated photometry, which was our contribution to this, which was the SED.
Okay, here we are.
And so in order to do this, we also broke down a little bit of the difference between the observations and the methodology by making mock SEDs from the CMD star formation histories. So these are two different methods that have very complementary systematics. So agreement is a really, really good thing. And so what we actually found with this is on the next slide, which is when we took all of the normalized star formation histories from the 36 galaxies in this study and took the median of that, we found both methods. I think we've got some feedback from somebody there. I'm going to assume that wasn't a question.
There was some background noise, unfortunately.
All right. Okay. Well, what we found is that there was actually a synchronization in the star formation where all of the galaxies seem to decrease and then increase in star formation at about roughly 6 and 3 gig years ago. So these are galaxies that are very far apart from one another. They're field galaxies to groups. They shouldn't be doing this, but Rubin is going to allow us to study this out to a greater depth of the volume, which is very exciting. So once we get the photometry from LSST and we supplement it with near infrared and CMDs from JWST, we'll be able to see how far out this goes. So thank you.
Hello, I'm Michael Rich, and I'm going to talk about the Blanco DCam Bulge survey. This is a survey using the dark energy camera at CTIO on the 4-meter telescope to survey 200 square degrees of the galactic bulge. This shows some papers, the two major papers, and Christian Johnson is the co-PI. Next slide. Next slide, thank you. Yes. Okay, this shows the bulge survey volume in yellow. We have data on all of the areas with that are circled. We surveyed the less extincted southern galactic bulge and get plus or minus 8 degrees in galactic longitude. Next slide. And this shows the color magnitude diagrams that we can achieve. This is calibrated de-reddened photometry spanning the entire bulge. You can see the double red clump, but for this whole region, we have been able to de-redden the photometry thanks to Simeon et al. De-reddening method, and we produce contiguous color magnitude diagrams. The bottom panels are de-reddened. The next slide. We have 26 known globular clusters. For example, we were able to show that FSR 1758 is not a dwarf galaxy. It's a metal core globular cluster. You can see the Gaia vector point diagram in the middle. So we've matched 91 million stars to Gaia EBR3. And in the right, we have the cluster color magnitude diagram for FSR 1758. We also have many other globular clusters. The next slide shows that we have U minus I 0 calibrate plotted versus FE over H. This is a plot of U minus I versus FE over H from Buckley et al. 2017. There's a nice correlation. Next slide shows that we can use this correlation to derive the abundance distribution of 3 million breadcrumb stars. So we have 250 million stars with UGRIZ-wide photometry, and we have 3 million breadcrumb stars with abundances accurate to point TDEX. And we show that in the bottom of the, near the plane, there's a simple model, one zone simple model, which changes dramatically to a metal core distribution at minus 8 degrees. Thank you.
Can I remind everyone to mute if they're not speaking also? Thank you.
Yeah, hi. So I'm Firoza Sutaria from Indian Institute of Astrophysics in Bangalore, India. And I'll be talking about one little topic which I think has been a little bit overlooked in this LSST planned survey. That's about searching for optical counterparts. I'd originally said that it would be about optical counterparts of soft gamma ray repeaters with LSST, but I realized that even other neutron star phenomena seem to have been overlooked, where for neutron star phenomena, I'm including things like isolated neutron stars which are not really pulsating, seen in compact objects, in binaries, magnetars of all kinds. Now, it's an interesting fact that while we anticipate that there are nearly 10 to the power 9 a billion neutron stars in the galaxy, the observed number of objects is only 10 to the power 3. And for them, the optical counterparts that are known are only of about less than 50. Okay. So, we have these very strong magnetic field neutron stars for which the magnetic field exceeds the quantum electrodynamics limits. Only about 30 such objects are known. These are magnetar counterparts. And these are the, they're seen from their X-ray and gamma ray emission. They're bursting giant flare objects. It's questionable exactly what the origin of these objects are. There's still several kind of models which are used to propose them. And optical observations, especially in the short wavelength optical observations, are extremely essential to constrain the theoretical models of emission from these objects. Okay. So, likewise, we also have the CCOs, the X-ray bright, optically very faint objects, non-pulsating objects, etc. These are they're X-ray bright, very optically faint. They are associated with supernovae remnants. Yes, we know this by spatial association, but once again, we need to know what the optical distribution is like. What LSST will end up doing for these kind of objects is basically that you could ask why we haven't been able to identify them. The fact is that they are very faint, around 20. Typically, optical magnitude is around 24th to 25th magnitude for most of these in the R band. And it's rather difficult, even with the conventional telescopes, to chase these objects down to that level. We're looking at the integrated magnitude. I'm not talking about pulsations from them. So you have 24 to 20. So, with LSST, we'll be able to reach down to 24.5 in a single visit. With multiple visits, go to 27. Could we move to the next slide, please? Next slide. Yeah. Search for variability in the optical counterparts. Obviously, we're not going to be able to see pulsations because, like I said, the period is anywhere between 1 to 11 milliseconds just for the magnetars. Most pulsars will vary anywhere between 0.01, a few 0.001, few milliseconds, etc., down to 100. So have I run out of time? So what we expect to see are various features around them. And if you go on to next slide, I'll just discuss about the other options that we've got over there. Yeah, we can also use the LSST integrated survey to search for companions of so-called isolated millisecond pulsars, basically answering the question about how long these objects have been evolving, but whether you are really isolated or not. So I'll end over here. I see you moved on to the next speaker. Thank you.
Thank you.
Okay, my name is Basílio Santiago. I'm going to talk about ultra-cool dwarfs, or UCDs, which are very low mass stars or brown dwarfs of spectral types M, L, T, and Y with very low luminosities and cool atmospheres. So my collaborators, students, and myself, we have created a code whose name is not very original, GalMod brown dwarfs, which is a Python code that computes the predicted number of ultra-cool dwarfs for a given survey and also creates synthetic samples of these objects. So it's an empirically based type of code in the sense that it uses quantities which are closer to the observational sites instead of using initial mass functions and star formation histories, which are pretty much unknown for this type of object because they're very low luminosity and low mass and difficult to detect. We're using local space densities for the different spectral types and a prescription that tells how these densities vary across the galactic volume. We currently use a double exponential profile for the thin and thick disks, which are the most important components for this for these samples. We also have intrinsic absolute magnitudes in different filters and cosmic scatter for each spectral type. A Redring law currently we use Schlegel et al. And also the survey parameters for the sample we want to synthesize, like the area, the limiting magnitude, and so on. And so these are the ingredients. In the output, we have true distances and apparent magnitudes in a set of optical and near-infrared filters, besides expected numbers of UCDs as a function of magnitude and colors. And also we have observational magnitudes and colors, which we take from a Gaussian error distribution whose standard deviation increases according to some prescription for fainter magnitudes. Next slide, please. So here I show on the top left the distribution of a synthetic sample with true magnitudes brighter than 23 in the Z band and the observed magnitudes in green. On the top right, the distribution is a function of spectral type for the same sample. Absolute magnitude is in the Z band as a function of spectral type, and the error distributions between true and observed magnitudes in the bottom right. Next slide, please. So we have used this code to obtain a model sample of UCDs, to model the distribution of UCDs from the dark energy survey year 3. and obtain a scale height estimate for those objects, and also to estimate chance alignment probabilities for binary systems involving UCDs. And we're planning a simulation with LSST. Thanks.
Hello, my name is Konstantin Malanchev, and I'm going to present you light curve analysis toolbox. It is high-performant feature extraction code written in Rust. Rust is a modern, memory-safe, performant language. Of course, it has Python bindings, which are already used by two ZTF and future LSST brokers, namely Antares and Ampel. So we wrote this software and worked on anomaly detection problem for ZTF, and we had to analyze millions of light curves and found that feature code we could find for Python are too slow for this problem. Next slide, please. Can you show next slide? Thank you. So this code provides 35 feature extractors, but actually you can have more features because some of extractors give you several values. For example, linear fit gives you linear slope, its error, and goodness of fit, so 3 values in total. And some of feature extractors are parametric, so yellow, marked yellow extractors are parametric extractors. And moreover, the code provides you a DMDT map plotter. DMDT map is a way to represent your light curve as a 2D image in 2D space of delta magnitude, delta time. And these DMDT maps are used in machine learning task for classification and anomaly detection. Next slide, please. So I said that the code is high performance, so there are a few notes about it. So we found it that it is something like 20 times more performant in some fixed feature set than fits. It is Python code, and majority of features of simple non-expensive features can be found in less than 1 millisecond, while MCMC feeds for reasonable number of samples, for example, for few thousand of samples, working only a few milliseconds, and protogram performance is good too. It is 20 times faster than AstroPy's implementation. And code is pip installable, so if you're lucky to have Linux or MacOS on x86 processor, you don't even need Rust to install it. And please go ahead and try it and write any bugs or any feature requests on our in our GitHub repository. Thank you.
I guess we have time for questions now.
Do we have any more speakers?
Nope. Kelsey was
Okay.
the last one.
Okay, very good. We'll open up to questions. You can just unmute yourself and ask your question if you would like.
Chuck Clater here. I have a question for Michael Rich.
Yes.
Michael, interesting talk. I'm curious to know, since you were observing in the galactic bulge, it's all crowded field photometry. So actually I have 2 questions. First of all, what software were you using to do the crowded field photometry? Second question is, when you were doing the final photometry, how did you correct for the galactic extinction and reddening, and did you use a localized model? I am a friend of Abby Saha, who's been using our Lyrae stars to do localized reddening and extinction corrections. And I'm wondering if you applied some of that methodology to your photometry.
Yes, first of all, the code was developed by Christian Johnson at Space Telescope Science Institute. It uses DAO photo. It's a PSF fitting code. He did all the analysis, including the photometric corrections, so that everything you take the photometric data taken in photometric conditions and calibrate the entire data set to photometric conditions. We then used the reddening model from Simeon et al., which is similar to Simeon et al. 2017. This is using the red clump stars, so it's on a finer 1 arc minute scale than was done by the VVV project. Now, the RR corrections do have the advantage that they can better correct for variations in the ratio of total to selective extinction. And down the road, we would like to do an SED-based reddening correction method, but we feel this is a good start when we see the quality of our color magnitude diagrams and the improvement in the U-band. We're very confident that we're doing okay on the reddening. We were in touch with the LSST project. I actually visited Washington, and we were able to show that our code was, the Christian's code was much more successful in detecting point sources than the standard crowded field photometry codes used by LSST, but then, those codes have improved. And so I would, if you would like to ask detailed questions, I would point you to Christian Johnson.
Thanks, Michael. That's very informative, and I appreciate your response. So
and also, I'm happy to ask if you have any intermediate questions. I can certainly point you to the references and so on, and what exactly we do. So.
Michael, there's another question in the Zoom chat.
Yes. Let me just bring that up here. There was an initial publication that I believe by the VVV group that thought that because of its extent, spatial extent, it might be a dwarf galaxy. It's relatively extended on the sky. Another result, by the way, I didn't have time to put in, is that many of the globular clusters that have been claimed by some people in the VVV group have turned out to not be confirmed when you add in both the U-band photometry and the Gaia EDR3 constraints. So many of those globular clusters go away. But this one is, it turns out when you have the benefit of being able to do a proper motion selected sample, you look at the color magnitude diagram, and the overall morphology of proper motion selected stars, then it does look like an old metal core globular.
There is a comment in the chat that recent spectroscopic analysis support the GC nature, globular cluster nature of this object too. From
thank you very much. I look forward. In fact, I'll click on that and take a look at that very interesting paper. Thank you.
Any other questions?
Do we have any additional questions?
Maybe I can ask one for Kostya. I was wondering what your plans are regarding updates of your list of features that are included.
You mean kind of update a feature while we have new observations? Sorry.
No, I mean just different features that you compute for the light curves as they are proposed in the literature, for instance.
Yes, most of the features are from literature and names. I use literature names where I can, and we will promote new features soon with my student, but not now.
Okay, but so you will move on as they come along, or do you plan to have like a yearly upgrades or something like that?
Yeah, we will upgrade the library with the new features. So it is ongoing process. So for example, we are looking for some features to separate outbursts or other upper side eclipse for variable stars, something like this.
Nice, this can be very useful.
I had a question
Okay.
for Charlotte Olsen.
Okay.
Your results are quite interesting. Have you compared them with the M31, the star formation histories for M31 dwarfs? It seems like the M31 dwarfs may not be consistent with that overall star formation history, which is interesting.
So actually, a lot of the M31 dwarfs are in this sample. So
Oh, really?
Yeah. So that's been part of that was part of the analysis.
So which star formation do you do your own star formation histories then for those?
So the CMD-based star formation histories were those that were published by Dan Weiss, I believe back in 20.
So you used Wise's star formation.
And then we did our own SED fitting. So the SED fitting was based on photometry that was made public with Johnson et al. From 20.
Yeah. I'm sorry to interrupt. It's time to switch rooms. So I believe if you go down to the bottom to the leave room or to the breakout room session, you can pick another room to go into. Speakers, thank you very much. If you hold on just a second, we'll welcome a new round of people. If you guys wanted to continue your conversation, that would work as well. So anyway, thank you everyone for coming.
Thanks a lot.
And we'll see you soon.
Have you compared made a plot of your star formation histories versus Wise's star formation histories from the SEDs?
May I suggest you continue the discussion on Slack?
Okay.
We will need
Yes.
to move on. Sorry about that.
And Charlotte, I just downloaded your paper.
Awesome.
I'll try to find a way to continue it, but we don't have a Slack room, right?
We don't, but you should be able to search me on Slack individually, and I can try and find you right now too.
Okay.
But yeah, I can also copy the paper as well.
There's a generic RBB Slack room.
Perfect. Yeah, I can do that.
I have a question for Costa.
And I have a question for you, but you was first.
Okay, thank you. So I need to know, can I use your your code to do power spectrum analysis of light curves?
Not right now. No, unfortunately, not now. So only in terms of spectrum of power spectrum, only periodogram is supported. So no support of after correlated function, for example, but it is in plans. Yes, okay, so we are going to implement, for example, after correlated function or correlated function for different colors.
Okay, great. Thank you.
I don't know if I still can ask a
yes, please
question.
Go ahead. Yeah, go on.
What is the typical time scale given by theory for optical counterparts of FRBs? So how long?
The fast radio bursts. Yeah. So how long should you expect to see an optical counterpart after the FRB?
Yes.
Well, let's see. For the latest FRB SGR association, that is 1935 plus 20 plus.
Okay, oops, I'm sorry, I wasn't.
We do not really see an optical counterpart of. Unless you take really deep observations, we're not going to be able to see them. Sorry, my internet connection went off. Could you get the answer, or can I repeat it again? What I said was that on the same night as the latest FRB SGR association came about, that's 1935 2154 SGR with an FRB, I did observations of the field of view of this SGR, and I do not see an optical counterpart. So theoretically, we do expect to see an optical counterpart, which should have brightened within maybe a few hours or so. And the brightening would have continued on for a few days, as has been seen in the case of previous giant flares from SGRs like 1900 plus 04. But in this particular case, even though there's an FRB, confirmed FRB and SGR giant flare connection, we do not see the optical counterpart.
Okay, very good. Very good discussion. We're going to get started again on the second round. Welcome to Stars, Milky Way, and the local volume. So we would like you to ask that you mute for right now. Please put questions in the Zoom chat. We're having a little bit of issue with the Slack questions. We will have time to ask questions at the end. If you want to go to the next slide. We, of course, have some friendly reminders, of course, for code of conduct and how you act, and then also interactions with everybody. So the talks are really interesting, and we're going to try to keep everybody on track. So let's get going.
You will see a countdown where my screen is right now, right? Like this.
Okay. Hi, I'm Charlotte Olsen. I'm a PhD candidate at Rutgers University, working under Professor Eric Goizer. And my talk is really to boost a really cool potential science outcome from Rubin, where we could potentially check to see if there is synchronized star formation in the star formation histories of local volume galaxies. And this is an extension of work that was published back in May, where we actually found evidence of synchronized star formation in these star formation histories of local volume dwarf galaxies. And these dwarf galaxies were part of the ACS Nearby Galaxy Survey Treasury, which is the angst sample, which is a volume limited survey, but these only go out to about a distance of 4 megaparsecs. And that's because that's about as far as you can get, resolved individual stars that would give you meaningful color magnitude diagrams. But they're far enough away that we could also get good integrated photometry. And this is really important because we were doing a comparison between two methods of star formation history reconstruction, which we can see a little bit on the next slide. And so the two methods essentially are from SED fitting, which is from the integrated, and color magnitude diagram, color magnitude diagrams where we have individually resolved stars. So these have complementary systematics, and they're using different types of observations. And so on the right-hand side, we have the star formation histories reconstructed from this. The CMDs that star formation histories that we have were already published and publicly available. And we just did our own analysis on the integrated SEDs and created the star formation histories seen on the right. We also decoupled the differences between observation and methodology a little bit by using mock photometry that had been generated from the star formation history from the CMD to see what's a methodological versus maybe a systematic coming from. Okay, but anyway, any agreement is going to be a robust agreement, and so on the next slide we show that we did actually find agreement between these two types of star formation histories for all of these galaxies. When we normalized all of the star formation histories and took the median, they showed a decrease and then an increase in star formation at about roughly 6 and 3 gig years ago. So this shouldn't happen. They're all separate from one another. Some of them are field galaxies, some of them are in groups. But with which will allow us, once we supplement it with near infrared and also CMDs from JWST, to push further into the local volume and see how far this extends. Thanks.
Thank you very much. And next.
Yes, I'm going to talk about the Blanco DECam bulge survey. This is a survey of 200 square degrees of the galactic bulge of UGRIZY using the dark energy camera at CTIO. And the two key papers are listed below. The next slide shows the footprint of our survey superimposed on the southern galactic bulge. And you can see the yellow outline is the area that we have produced and de-reddened. And we have data in the other fields, including the Sagittarius dwarf spheroidal galaxy. The next slide shows our color magnitude diagrams, which have been derived from PSF photometry using a DAO-based code developed by Christian Johnson. And the reddening is accomplished from Simeon et al. 2017. Based on the VVV method. Next slide shows that here is a globular cluster. We have 26 globular clusters. We have U-band photometry, which allows us to see multiple populations. We also can make use of Gaia EDR3. Here's an example, FSR 1758, once thought to be possibly a dwarf spheroidal galaxy, turns out to be an old metal core globular cluster. We also find that some of the clusters claimed by Maniti et al. To be globular clusters do not stand up to scrutiny when the Gaia EDR3 is applied. The next slide shows that we can use the UV channel to derive a correlation between U-I de-reddened and FE/H as measured by the high-resolution study of Zocoli et al. 2017. This has a roughly 0.2 dex spread in FE/H, spanning -1 to +0.5 dex of the entire metallicity distribution of the bulge using red clump giants. The next slide shows that we can derive abundance distributions across the galactic bulge using this method. So we now have 3 million red clump stars with abundance distributions. And the red abundance distributions are from spectroscopy. The gray is from our derived abundances. And then on the right-hand side, you could see that near the galactic plane, the one zone simple model fits the abundance distribution. The stars are more metal rich. The distribution becomes bimodal as we move away from the plane. And at -8 degrees of kiloparsec away from the plane, there is a distinct shift in the shape of the stellar abundance distribution seen clearly for the first time. Thank you.
Yeah, hi again. So I'm Firoza Sutaria from Indian Institute of Astrophysics in Bangalore, and I'm here to discuss about this very often overlooked potential of the stacked LSST data with respect to searching for optical counterparts of various kinds of neutron star phenomena, including isolated neutron stars, central compact objects, neutron stars and millisecond pulsars in binaries, and of course, magnetars, both AXPs and SGRs. So the fact is that all of these objects in the optical bands are extremely faint with the R magnitudes of the order of 24 and greater, V magnitudes and B magnitudes fainter than that, going on to 25 and greater. The detections are necessary in order to confirm or dispute various emission models. In fact, it turns out that at one point in time, we used to think that magnetar emission would be in the optical and infrared bands would be purely thermal in nature. But recent observations of certain flaring SGRs and their optical counterparts have demonstrated that most likely there is very little thermal contribution to this. Much of even the optical emission is possibly being reprocessed, is possibly X-ray emission that is being reprocessed in the magnetosphere. The faintness has made it rather difficult to track even the bright AXPs and SGRs in the optical. And so this is a place where LSST, even in a single visit, would definitely make significant contribution with single visit magnitudes of 24.5 and stacked data will, or even over one night, will take you down to 27. Next slide, please. So in the next slide, I would like to point out that in addition to detecting the optical counterpart of the SGR itself, there will also be other optical counterparts of the various infrared relics that we have seen, for example, in the case of certain of some SGRs, some magnetars. For example, the dusty ring around the SGR 1900, there's been a ring detected. There's always been a question about SGR supernova remnant association and the progenitors of magnetars themselves. They are theoretically supposed to be fairly young neutron stars, but not all of them have a confirmed supernova remnant and magnetar association. Therefore, the detection of rings like this makes it very crucial to determine whether these objects are really truly young magnetars, truly young neutron stars or not. Moving on to the next slide, the final slide. There is also the question of the integrated LSST data, the stacked LSST data, and even one-visit LSST data being used to answer this truly vexing question: is there truly an isolated millisecond pulsar? At one point, we did think that certain millisecond pulsars were isolated. This is my own observation taken with VLT several years ago, in which we were looking for optical counterparts of J1744 and 1024, both of them millisecond pulsars. And we didn't find the counterparts themselves. We did find some faint neighboring stars. And subsequent long-term observations of these objects has shown that there are long-term counterparts to it. So LSST will contribute. Thank you very much.
Thank you.
Okay, my name is Basílio Santiago. I'm a member of the Brazilian participation group. I'll talk about a Python code that makes synthetic samples of ultra-cool dwarfs, or UCDs, which are very low mass stars or brown dwarfs of spectral types M or later. Very cool objects. The code is called GAU-mod brown dwarfs, and it uses empirical quantities as ingredients, such as the space densities as a function of the different spectral types in the immediate solar neighborhood. A spatial profile, three-dimensional. We use the double exponential profiles for the thin and thick disks. Absolute magnitudes and intrinsic scatter as a function of spectral types. A Redwing law and the sample parameters such as the survey footprint, the limiting magnitude, and so on. And in the output, the code delivers expected magnitudes, number of UCDs as a function of magnitude and color, as well as a synthetic sample with true and observed quantities such as distances, magnitudes, and colors in several filters in the optical and infrared. Next slide, please. So here we show some example plots. In the top left, the distribution of apparent magnitudes, both true and observed, limited at true magnitudes brighter than 23rd in the ZMAG in blue, and the observed magnitudes are in green. On the top right, the distribution of UCDs is a function of spectral type for the sample, for the same sample, where 10 means an L0, 20 means a T0. On the bottom left, absolute magnitudes in the Z band is a function of spectral type with some scatter. And in the bottom right, the difference between observed and true magnitudes for some prescription of magnitude errors. Next slide, please. So the code has been applied so far in the context of the Dark Energy Survey, of which we are members. The code was created not only by myself, but also by collaborators and students. So in Carneiro-Russell 2019, we modeled the spatial distribution of UCDs using data from the DES year 3. And in Del Ponte et al. 2020, we estimated chance alignment probabilities of binary candidates involving UCDs. And of course, as members of the BPG, our next step is to simulate a full LSST sample. Thank you very much.
Hello, my name is Konstantin Malanchev. I'm from University of Illinois, and today I'm going to present you light code for analysis Toolbox. It is high-performance feature extraction code written in Rust. Rust is a modern, memory-safe, high-performance programming language. Of course, the code has Python bindings, which are used by two ZTF and future LSST brokers, namely Antares and Ample. And the code was developed when we faced a problem of feature extracting of millions light curves of ZTF to detect some anomalies. So we decided to develop our own code, which will be more performant than existing ones. Next slide, please. So here you can see different feature extractors. Totally, we have 35 feature extractors, but you can have more features because some of feature extractors, for example, linear fit, provides you several values. In the case of linear fit, it is linear slope, its error, and goodness of fit, so 3 values. And some of the features are parametric. Parametric are yellow here. For example, you can ask for different n value in beyond an STD feature. And moreover, the package including DECam map plotter. DECam is a light curve representation to delta magnitude delta time space, which is used for classification and anomaly detection. You could see in the center that different types of light curves are presented by different patterns in this DECam space. Next slide, please. So I said that the code is high performance, so we tested it against other codes and found that it is faster than, for example, FIT's code, which is popular feature extraction code in Python. Periodogram implementation, namely fast and obscurable periodogram, is something like 20 times faster than AstroPy implementation. And we tried to make even a parametric fit functions like Basílio function fast, and it takes several tens milliseconds to fit supernova light curve. The package is pip installable, so go ahead, install it, and if you find any bugs or would like to us to make some new feature extractor, please point it in our GitHub. Thank you.
Okay, I believe that's it for the speakers for this session. Do we have any questions? You can put it in chat, or I believe there's enough people that we can actually unmute yourself and ask a question if you are comfortable doing that.
I have a question for Mike. So Mike, actually, I can control the slides, so this is convenient. I can go straight to the figure, this one here. So can you remind us what different coloring schemes represent here? So you have blue, white, and yellow regions. So
oh, okay. So the yellow are completely reduced frames that where we have run our code and completely reduced the data. The field is irregular because of difficulties with the path and getting the field completely done. White is the Sagittarius fourth toroidal galaxies, galaxy fields, not yet reduced. We did not get NSF funding, so we are labor limited. The blue fields are fields in the Milky Way disk that we took that are designed to be used for statistical subtraction of a disk foreground field from the bulge in the yellow region. So the idea is to statistically subtract the disk foreground in an effort to constrain the age of the black bulge.
And so are you worried, though, that the extinction variations across the line of sight may make subtraction quite problematic using fields that are significantly far away?
Our first preference in isolating a sample in the bulge is to use Gaia parallaxes and proper motion cleaning, following the methods outlined originally in Kuiken and Rich 2002. However, Sokoli et al. 2003 and other papers, beginning with Ortolani et al. in 1993, did successfully use statistical foreground subtraction even though, given many problems, it does have the advantage of not requiring a kinematic or proper parallax-based selection. Perhaps by the end of the Gaia mission, parallaxes will be so good that we can meaningfully exclude stars from the bulge closer than 4 kiloparsecs. But we took those fields just in case. They have not yet been reduced with our final PSF fitting code.
Do you have any time resolution in your images, like time series of any sort, or are they just?
No, the work of Saha et al. Is the gold standard for time series. He was interested in our Lyrae stars and covering, being that we wanted to cover all the possible colors from U, PRs, I, Z, Y, and getting this significant span of 200 square degrees spanning the whole southern galactic bulge mass, the mass of the galactic bulge. We couldn't also get time series, regrettably. We would love to come back and actually do ground-based, a second epoch or ground-based proper motion measurements, but down the road, of course, the Rubin Observatory will provide that.
Yes, I think more data spread over time would be particularly useful in the case of LPVs.
Absolutely. Now there is, in Gaia EDR3, I am told, I haven't looked into this, there is a variability flag, and there may be a very nice sample of LPVs that can be derived from Gaia, but I don't know about it. Obviously, it would be one of the things that I've advocated for in the cadence for the bulge is an LSST cadence that would make possible the discovery of Myras from periods 100 to in excess of 1,000 days.
Nice, thanks, Mike.
I'm certainly open to, also this is an open collaboration. Individuals interested in joining the Blanco DECam Bulge Survey project be most welcome. And we continually propose, we have not been successful recently with NOIR lab.
So if I might interrupt, Mike, this survey is purely a photometric survey, an imaging survey, or are there spectroscopic elements to it as well?
There is not a formal spectroscopic component. There are going to be a large number of spectroscopic surveys, and one of the, coming up, you'll have moons and also foremost. And one of the difficulties is that Christian had access to Magellan and M2FS through CFA, but now he's at SDSCI, so that access is less robust. But we are looking at possible, once we do further analysis of the data set and proper motion cleaning, there will be subsets of the data that we will definitely be interested in following up spectroscopically.
Okay.
It's just a problem because unfortunately, there is not a lot of support for multi-object high-resolution spectroscopy for the general astronomical community of the United States.
Yeah, that is true. But wouldn't medium resolution spectroscopy also do? I mean, how high resolution do you want to go to? I'm just thinking in terms of, say, extinction studies along line of sight, using, many of these.
I think that the potential for medium resolution spectroscopy, well, I think that first of all, with our broad wavelength coverage, we should be able to do an SEV-based extinction corrector that is superior to what we have at the moment. But that's going to take labor. There will be facilities coming online like PFS on Subaru that are able to do, for this to have an impact, there is already thousands of spectra in the region of the galactic bulge that could be retrieved from various archives. So in order for this to have an impact, we have to look at something like DFS that itself has 2,400 fibers available in a single shot. And we do plan to propose for that facility. What we really need, though, is higher resolution spectroscopy. That's only resolution of 2,400.
Okay, thank you.
I think we have time for one more question, potentially. We've got about 2 minutes left, 1 minute left. I thought the talks were very, very interesting, and I'm going to go read some papers now.
I also want to acknowledge Patricia Whitelock's, of course, the landmark papers by Robin Cashbowl and her collaboration are the gold standard in the subject. And we did not consider taking on that just because we knew about this and didn't have time.
No more questions or comments, apparently. Last chance.
Okay, well, I have 11:30. Everyone, the session is over. Thank you, moderators, as Melissa just said. So I appreciate everyone's time. Thank you for coming.
Thank you.
Thank you.
Everyone. Take care.